Okay, so let's talk about LIBS. I don't know if you know what is LIBS. LIBS is laser-induced breakdown spectroscopy. So laser-induced breakdown spectroscopy, spectrométrie de plasma induit par laser in French. And my research topic is really axed to imaging. So that will be a big part of the lectures. But I will start to present you the principle. And let's say in few slides, the general concept of LIBS measurements. So in LIBS, basically, you focus a laser pulse on the sample, and then you will ablate a little part of matter that will conduct to a plasma formation like microstars that will emit a lot of lights. And beyond these lights, you will have the relaxation, the cool down of atoms, ions, that will go back to their fundamental level by cooling down. And in this process, you will have the emission of a lot of photons that will be very characteristic, very precise energy related to the atomic structure of the atoms. And if you collect the light with an optical spectrometer, you will record an emission spectra where, so the emission lines that you will see will be very specific to the elements, and the intensity of this emission line will be related to the concentration of these elements inside the sample. There is a very emblematic application of LIBS. I'm sure you already heard about LIBS, because for 10 years now, LIBS is equipping the rover from the NASA for the Mars exploration. So there was 2 rovers, Curiosity and Perseverance, and we will go back later, but the head of the rover here is a LIBS instrument called ChemCam and SuperCam later. It allows to focus the laser at a certain distance up to 10 meters and to analyze the composition of rocks in the vicinity of the rover. But I will talk a little bit more later on this. So now if you want to characterize the plasma in general, you will use the 2-dimension scale where you represent the plasma temperature on one axis and the plasma electron density on the other axis. And then you can see from these figures that you have a very large panel of plasma from the sun core to just a flame. And the laser-induced plasma, so the plasma that are interesting for us, are very similar to spark. So we will work in general with temperature in the range of 10,000 Kelvin and electron density in the range of 10 to the power 17 per cubic centimeter, just to give you the order of magnitude. So it's quite similar than sparks. And there is something very magic with the LIBS technique and the capability of this approach to measure the elemental composition. It's like the shampoo that you can see in the advertisements. There is 3 effects in one. Your laser pulse have 3 effects. The first effect, it allows to sample a part of the matter. So it's in general microgram, not too much. And we will see that we can go much below this microgram later. And this matter will be atomized by the photons of the laser pulse and then excites. So these 3 phenomena will arrive almost simultaneously from only one laser pulse. And if you can look here in these figures, we are generally using nanosecond pulse because with nanosecond pulse, we have enough time to atomize and excite very well the matter. And this conducts to a very hot plasma that will emit a lot of lights. So the ablation occurs very, very quickly at the scale of a fraction of nanosecond. And then the matter is extracted at the sound speed, more than the sound speed, so it produces a shock wave. You also have thermal diffusion a little bit on the matrices. And then the rest of the impulsion will interact with the ablated matter and will hot it. And the step that will be interesting for us, it's the cooling down, the relaxation of this plasma that occurs in the range of 1 microsecond after the laser impact. And then there is the expansion, the emission, and finally the recondensation and the cooling down, and no more emission at this stage. So laser-induced plasma is a fantastic source for spectroscopy, but also very complex in the sense that we have a highly transient object. At the first moment after the laser impact, you can reach the 50,000 Kelvin in terms of temperature. So you have a very, very hot plasma. And at this moment, you cannot see the elements. You just see the brainstroom and the effect that give a strong continuum emission. And in few microseconds, you can see that the temperature will be decreased by almost 1 order of magnitude or even more. So this is a highly transient object. And depending on the time for which you will look, the emission, you will see very different things. So at the first moment, as I said, you can have a strong continuum, then the ions, atoms, and even at long delay, you can observe some small molecules like radicals that will be related to the recombination of atoms inside the plasma. So here you have a typical LIBS spectra obtained at different integration delay. You can see at the first moment that you have a very broad lines, high continuum, and then the continuum progressively disappear. And at this stage, you only have good emission lines. This is why if you have the money, if you are rich, the best for LIBS is to use ICCD detector. I don't know if you are familiar with this detector, but it allows you to really record very accurate temporal window. And so in this example, the best temporal window is the one that giving the red spectra here. And in this case, it's at about 1 microsecond after the laser impact. Okay, so here you have a very nice plasma obtained on the glass. And I just wanted to add some physics in these lectures a little bit. So there will be very basic law that you may know to explain the plasma emission in terms of elemental or ionic emission. And the first law is the Boltzmann law that will manage the emitter populations, and then that will be directly related to the line intensity measurements. So this Boltzmann's law say that the intensity that you measure will be proportional to the total number density of the elements that you are working. Some atomic parameters, A and G, the partition function, U, and the Boltzmann law that you know as a function of temperature. And all these coefficients, atomic coefficients, you can easily get them in some atomic database, and the well-known database is the NIST database. You have access to it very quickly from Google. So in the NIST database, you can, for example, enter the elements, the species you want to see, etc., made some filters, and you will have a table. So here, this is a very small table showing some lines of aluminum in a very reduced spectral range, around 300 nanometers. I just wanted to show you that for each element, you will have, in some case, 2 or 3 lines, in other case, thousands of lines, and each lines will have different atomic parameters and so on. But I will go back later on this. So this Boltzmann law is the first law, and it's valid only if your plasma is in local thermodynamic equilibrium, which means that basically all the species inside the plasma are at the same temperature. So it's easy to fulfill this condition. And the second law is the SAR law that will give you the proportion between atoms and ions, basically. So you just apply this formula and you will have the proportion of ion with regards to atoms. And basically more complex, in my point of view, since you have a lot of ions, electrons inside your plasma, you will have a very strong Stark effect that will affect the line shape that you will measure. In particular, the Stark effect will affect the width of the line and the shape of the line, because this Stark effect has a Lorentzian profiles. So I just show here an example. This is a spectrum, very old spectrum, that was recorded on a potato. And you have the hydrogen line, H alpha, at a different detection delay. And at very low delay, you have a very strong electron density, while at long delay, you have a smaller electron density. So you can see here the influence of the electron density on the line shape for the hydrogen lines. That is one of the lines the most affected by this Stark effect. So you can see the narrowing of the line when the electron density reduce, and also a shift of the line to the left in this case. That is also related to the Stark effect. On the left, here you can see some calcium line that appears more Gaussian. I don't know if you are familiar between these profiles. It means that in this case, we are limited by the resolution of the spectrometer. That is almost very similar to a Gaussian function. So basically, all the lines that we will measure will have the contribution of the Stark effect, which is Lorentzian, and the spectrometer response that is more Gaussian. So if you want to model a lines in a LIBS plasma, you will use a Voigt's profile, the convolution of 2. That's all with the physics. Let's talk about marketing. Why LIBS is so fantastic? All the advantages of LIBS. The first advantage is that you have no contact with the sample. It's not so bad. this works with any type of material. You can, of course, it's better with solid, but you can analyze liquid, inside liquid. Some group, they have developed LIBS instruments to go inside the oceans for archaeological findings on all ships and so on. It's working. But you can also analyze in the air, no problem. This is a measurement in ambient condition. In fact, I think this is the only technique that is able to measure the elemental composition in ambient atmosphere. And you have a minimum sample preparation. I don't really like this one, but in fact, this is true. For example, for Mars, you can see on this photo that the surface of Mars is very dusty, okay? You have dust everywhere, recovering all the rocks. And so the advantage here is that with laser ablation, you can shot several times at one position of the rocks. You remove the dust in the first shots, and then you continue to dig inside your rocks. And so that was a very strong advantages for the Martian exploration mission. And in general, the NASA team, they are doing 5 shots to remove the dust and then 25 shots to go deep inside the sample. Then another advantage is this is an all optical approaches, very similar to a microscope, basically. And you have here on this photo, you can see the microscope lens that will focus the pulse. It's not easy to see, but you have the plasma here, the sample, the XYZ stage, the collation optic, and in general, we are also using an argon flow to work in an argon environment. Why? It's because when you are in the air, you need some energy to break the bounds of oxygen and nitrogen. While in argon, this energy goes directly to your target. So we also always have better signal in argon compared to air. But it's still in ambient atmosphere. And the 2 last advantages that will be developed in detail in the rest of the lectures is the microsampling capability. It's like optics, so you can focus your laser beam at the limit of diffraction, and so do very precise and accurate microsampling. And you can also image by reproducing this measurement at different position of the sample. So that was the advantage. Now the drawbacks, the difficulties, there is a lot, in fact, because you have to know that this technique is not new. This technique is quite old. It was probably one of the oldest elemental approaches. It just appears 1 year after the first laser in 1963. So it's very old as an approach. But as I present it, I'm presenting it like it is a new technique and so on. No, it's not true. It's a very old technique. For most of you, you did not heard about this approach before. So it means that this technique is not so easy, as I said. And you have some strong difficulties with this. The first is the signal complexity. You have a spectrum here. That's just one element. If you look at this signal, you can even say, no, but this is not signal, this is noise. I don't know what you think, but it looks like very, very noisy. If you zoom here, you can see that there is a signal and there is emission lines. So this is molybdenum. Molybdenum is more than 15,000 lines. In some cases, it can be quite complex to process the spectrum. Here, I want to emphasize on the reproducibility issues. You have a laser, you have a lens, you have a spectrometers, you can very easily get a LIBS spectra. It's very easy. But what is complex is to reproduce it. And the reproducibility issues is one of the most drawbacks of these approaches. And I wanted, with this video, to show you the evolution of the plasma while the laser is firing at the same position. So here you have an aluminum plate of 1 millimeters and some air here. And then this is a polymer. And the laser will fire from the top to the bottom. Let's go. It's 10 images per second, 10 pulses per second. So as you can see, the plasma shape really changed, let's say, dramatically. And then you go through your 1 millimeter aluminum. So it was just to show you that very easy to produce a plasma, but to be able to stabilize this plasma, to reproduce it in very stable condition is not so easy. And then a new slide for me. I was thinking to a slide that could be easy to understand. When you do analytical science, there is a term that's always coming. It's the matrix effects. So basically, the chemists, when they observe different signals from a different matrix, but the signal should be the same, they say, oh, we have a matrix effect here. And this matrix effect is really easy to understand if you consider the diamond and the graphite. These two materials are 100% of carbon, but they are very different by nature. And you can, I think, easily understand that it will be much more difficult to produce a plasma from diamond with regard to graphites. And then with these two materials, you will have a different carbon emission, while they are both 100% of carbon. So we have matrix effects. The signal will be really dependent on the matrix, meaning the composition, the structure of your sample. And so if you want to make quantitative measurements and then say, okay, there is 3% of silicon here, something like that, you need matrix match samples. Means that if you want to quantify the inside aluminum, you need a series of aluminum samples to make your reference and so on. And so in some case, you can do this. In some other case, you cannot because this matrix match sample does not exist. But in chemistry, this is a slide that I always show when I make a presentation in chemistry community. Because for the chemists, in general, they are considering that the LIBS is absolutely not quantitative because they heard that LIBS is not reproducible, etc., etc., etc. So I'm always showing these slides. You can do fantastic quantification with LIBS. And I was recruited in 2008, and my first quest was to show that LIBS could be quantitative. So I worked for several years to demonstrate this type of curves that show perfect linearity with different sample, with concentration and so on, and that gives, yeah, LIBS is quantitative. But I was naive, let's say, because you can do quantitative measurements, but at the price of many constraints. First, for this sample, that was glass sample, we had to make some preparation, meaning that all the glass sample were fused in fuse beds like lithium tetraborate beds. And then we had to develop a fantastic instrumentation, very complex, very stable, and so on. Find a good protocol, and 3 years after, we got these results. I mean that with these results, I went to analytical laboratories and say, hey, looking guys, we are very quantitative, this is fantastic. You have to buy LIBS, give me some money, I will give you a fantastic LIBS. And they say, no, we don't care. We already have anything we need. The technique they are using, they are maybe less powerful, whatever, but they are working and they are fulfilling our needs. We don't need your new approach, too dangerous. That was the conclusion. And for sure, today, there is a lot of analytical laboratories that are using well-approved, well-established technique like ICP, XRF, and so on for elemental analysis, and they don't need LIBS for sure. So the question was where we could bring LIBS. And in my point of view, there is two attractive domains for LIBS, highly attractive domains. The first one is the in situ analysis, like as I show with the Mars mission, the NASA. So this was the more expensive LIBS instruments for all times, $1 billion. But it works very well because for 10 years now, there is regularly like 50 LIBS spectra per day from Mars. And you have here the first LIBS spectra obtained on Mars. And so this instrument, the SHEMCAM head here, was developed by the CNRS in Toulouse in collaboration with the Los Alamos Institute in US, and use a telescope very easily that allows you to focus the laser beam up to 7-10 meters and also collect the lights. And then in the domain of the in situ analysis, there is also very strong development made by a lot of companies in the last years in the development of LIBS gun. So you can have here the possibility to have just a LIBS gun and do a measurement like this. And there are more industrials that more and more industrials that are buying LIBS gun like this that allows you to make prospection. So here we have a geologist colleagues that is doing prospection in the rocks taking. Here you have also another colleague working, in the characterization of archaeological materials. And for example, this lady made 2 years of measurements in the Notre Dame after the incident to measure all the metals in the different part of the cathedral. That was for the first domain. And the second domain is, let's say, my domain, is the microsampling and imaging. But this is only my point of view. So 1962, the first laser, 62, yes, 63, the first LIBS instrument. In fact, they realized that with pulse laser, it's very easy to break optics. You have a lens, you focus the lens, and you break your optics, and you create a plasma. And from this plasma, at this moment, 2 French ladies made a very good articles that is reported in the Matthew Baudelaire review here, showing all the capability of this type of measurements. And very shortly after the first demonstration of this technique, there was like 5 or 6 companies in the world, like Zeiss, who said, wow, fantastic approach to make microsampling. And so very easily, they put like a strong energy to develop the first LIBS microscope, which opened appeared only 1 year after the first LIBS demonstration. So it was very big developments. You have the microscope objective, the laser, the light collection with an optical fiber, and you shot. Unfortunately, this instrument was only sold in 2 or 3 exemplars, something like that, simply because at this period, to record the spectra, you need a photograph plate. So one shot with a laser that was not very stable, and then you put the photo, you develop the photo, you process the photo, and so it was not very easy and free user, let's say. We had to wait about 20 years ago. Basically, this corresponds to the appearance on the market of a new ICCD detectors that allows you to record a full spectra simultaneously, because before this period, the spectroscopics were generally using photomultipliers only at 1 wavelength. So with the ICCD, we got the first papers on mapping and imaging. And basically here, very recently after the first mapping papers, some group well-known in the LIBS community made some demonstration like kilohertz laser from the Fraunhofer Institutes, micrometer resolution from the CEA in Paris, large surface in Spain, 3D analysis in Italy, and so on. And then you see there is not too much paper. But from this is nice because you can see an inflection here, and we start to work on imaging in 2010. So it's maybe because of our research. And you have to know that at this period in 2010, something like that, we were extremely poor. No money, no laser, all spectrometer, no money. All the proposals for us were rejected. In the physics parts, they were saying, no, but what you're doing is too chemist. And in the chemistry part, they say, no, it's too physics. We know how it was difficult to get money from a project with this activity. And we were very lucky because in the ILM, there is a team that is developing nanoparticles for many purposes, artwork, many things, and also for medical applications. So these nanoparticles called AGICs are now today administered to humans for cancer therapy. And Olivier Tillman, so the manager of the FENEC team, asked us if we could image the distribution of these nanoparticles in tissues to study the toxicity of these particles and for example, the renal clearance. Are the particles well eliminated by the organism? Some type of questions. And then we say, okay, let's try. But honestly, it was very highly challenging at this period. The sensitivity required is very low. The speed, if you want to do imaging, should be very high. The spatial resolution should be low, and the data processing and so on biological tissues is what kind of headache. And I have to say that when I quit this meeting, I say, this will never work. But we try, and we got this. 2011, we were so happy. 3 pixels on an image. Okay, this is garbage for sure, but at this period, we were very happy. Yeah, we detect gadolinium in the kidney. This is mouse kidney. And the biologist colleague, they were, oh, yeah, this is very nice. And then they disappear. But from this, honestly, this is one of my favorite results because, of course, it's very bad and so on, but the challenge were very high. and we detect something. So the green pixel that you can see here is 2 or 3 times the limit of detection. They are very low. So basically, we were very lucky to see something. And from this little signal, we were able to improve the acquisition rates, the sensitivity, the resolution, the data processing. And finally, in 2011, so 6 years after, we reached the megapixel, 1 million of shots. So this measurement required like 4 hours of analysis. Exactly the same time that for this one. Here it's at 100 hertz, so 100 plasma per second. This one was at 0.1 hertz, something like that. I don't remember exactly, but and we were in the lab and so on. So that was a fantastic moment, fantastic time. And honestly, I was never happy with the results. This is why one day I say, okay, let's try to go back and take some image and make a kind of slide that will show our improvement. And this is the story of this slide. And from this moment, we start to attract the attention of many groups in preclinical evaluation, like Harvard, Fraunhofer Institutes, many groups in France. And we had the chance to participate to very high-level paper in this nanoparticle stuff. In fact, the biologists were really appreciating the capability of this imaging technique to screen all the organ without any labeling. And so we developed some biomedical application I will show more later. We also initiate many collaboration in the geological stuff. So there is fantastic opportunities in the geological fields. Here you have, for example, a speleothem. This is a stalactite or stalagmite obtained in a cave. And in this surface, you have thousands of years of history of paleoclimates. Here, you have research of strategic elements. You, I think, already heard about these strategic elements like rare earth elements and so on. And the final stuff was the industry. So we made some collaboration with different groups for crystal growth, for example, or catalysis with the IFPEN. And here you have an example of a thin film. So this D1 here corresponds to 20 nanometers of lithium lipon. And here I think you have 500 nanometers, things like that. So we got also some money from the region to create a platform that is named Optolyse, and there is also a part of Optolyse here in Hubert-Curien. And basically, but we also created a startup, Ablatom, in 2017. At the first moment, this startup, the plan was to make analysis, routine analysis. So they were locating our instruments in the lab. And then for the last 2 years, they start to sell instruments. And the first LIBS imaging instrument was sold to the IFPEN last year. And also this year, there is several orders. Okay. That was for the story. Let's go now to the instrumentation and the principle and so on. So the principle is quite very easy. It's like on Mars. You just focus your laser pulse on a sample. The only difference is there are two. You have to use a microscope objective to really focus your beam on the smallest diameter as possible, spot as possible. And the second is you have to move the sample as fast as possible while you continue to fire. So there is a video. So you can see the scan, so the laser is firing at 100 Hz, so you cannot see the flash, but I assure you that each plasma is has a duration of few microseconds only. We cannot see very well, but for each plasma, we'll record the spectrum. And from all the spectrum, then, we observe the emission line, we extract the intensity of these emission lines, and then pixel by pixel, we will build some elemental images. And this is what we can get at the end. So here you have a rat kidney in this case. The animal received an administration of intravenous administration of gold nanoparticles 1 hour before to be sacrificed. And then the biologists kill the rats, collect the organ. The organ was included in epoxy resin, polish, analyzed. And this case is 6 hours of measurements, a night of measurements, basically. So what you can see here, you can see that the nanoparticles are really at the periphery of the organ. It's normal for biologists. It's in the cortex region. It means that the particles are being processed by the organ. You can see the phosphorus signal. So the phosphorus is really present in the cell, and it indicates the cellular density. So it's cool to get this signal to see where the tissue is. And the iron is related to the blood vessels, basically. Some other example of preclinical studies. So we were also able to make quantitative imaging. In this case was gadolinium. 3D imaging of tissues by continuous ablation. So in this case, we made 20 consecutive maps on the sample. So for each map, you go down from 10 micron and you vaporize all your sample. And more recently, some tumor targeting to go directly on the tumor. And this will allow to optimize the nanoparticle fixation on the tumor. Okay, so now another example that is from a geological sample that was collected somewhere in the world. I don't remember, in fact. And the idea in this sample was to study the distribution of germanium inside the sphalerite. Sphalerite, this is ZNS. And in fact, in this sample, you have two mineral phases, sphalerite and silicate or quartz. And this is a very nice story, honestly. Because now I think we have 4 or 5 papers on this sphalerite stuff, and we receive samples from China, Australia, and the people really like such type of imaging. And at the beginning, I received a phone call, I think 3 or 4 years ago, from a guy that I didn't know at all in Montpellier. So the name is Manuel Munoz, professor there, and he told me, "Oh, Vincent, I'm very embarrassed because I have a PhD student and it just starts, and I learned that the synchrotron in Grenoble will be closed for 2 or 3 years. And in this PhD, I aim to make some measurement of germanium in sphalerite. So I was asking maybe you could do something. So, germanium. I never saw these elements. Let's try. And so I received very nice sample. And at the beginning, he told me, I need the measurements on, oops, sorry. I need the measurements only in this region. I said, no, but let's do everything. 6 or 9 hours of measurement, a lot of data and so on. And finally, we got this. And when he saw that, he said, wow. They made 3 papers only with this analysis. I'm not able to understand what they write, what they wrote. But no, honestly, it was a very, very nice story. Why? Because as I said, you have 2 mineral phases. So the sphalerite, the silicate, and here you have the germanium map. This is not true map, because in this case, you remember I told you about matrix effects. So we have matrix effect. We will not have the same germanium signal for a similar concentration in the both matrices. So the true strategy is to consider, okay, we will do some image processing. We will only take the sphalerite phase and we will process the germanium. That's this image in blue. And then now we do the same for the germanium in silicate, and I display it in red, 2 phase, 2 difference in signal. And basically, the geologists, they never saw germanium in silicate. So to make this big image allowed to demonstrate that there was some residual concentration of germanium in this silicate that was not expected. And finally, they did some quantitative punctual measurement with ICP-MS, and we were able to calibrate these two maps and to get the concentration map. Okay, so this is the instrument. So if you knows a little bit to play with optics, I think this is the case. You will recognize star-labs, cages, rails, and so on. And it looks very big, but in fact, it's just 1 square meter. It's not very big. It's a kind of custom microscope. The laser beam is arriving here, focusing down. Here we have a reflective objective. We are using a reflective objective because this instrument is coupled to a Raman also in system. So like this, we don't have any chromatic aberration. Here you have 2 collection lines, so 2 spectrometers connected with optical fibers, some pointer lightnings, and so on. And in fact, we also work a lot on the, let's say, protocol, data software, data processing software, and the control software of the equipments. So basically, we have the capability to move the sample to the left here and to image the sample in a microscopic way to get a very nice optical image of the sample. And in the software to select the sequence you want to do, the region of interest that will be imaged. And from that, then the instrument is totally autonomous. You can leave, take a coffee, go to sleep, make a nap, and so on. It's no problem. And there is also a Raman, but honestly, we are not really using the Raman. We are not experts. If you want to do a Raman mapping, you need 1 second per point, so it's 24 hours. So to resume, LIBS imaging is fantastic. I see that some of you start to sleep a little bit. Fantastic. LIBS imaging is totally crazy. If you want to give me some money, I will take, like as a support. No, I'm kidding. Today, we are working at 100 Hertz. with a resolution of 10 micrometer. It's not so huge, but it's not so easy also. With a limit of detection that is more important in the range of the ppm for almost most of the elements, but I will go back later on that. And you have a dynamic range for 6 orders of magnitude. So you can go to the ppm to the tens of % on the same spectrum. And it means, in my point of view, that really you can really consider this imaging approach in the very top state-of-the-art elemental imaging approach. That could be the synchrotron micro-XRF, that is the best technique for sure in terms of sensitivity, resolution, and so on. And the LA-ICP-MS also, that is the more developed elemental approach in laboratories. But we have our own specificities. Like I say, it's an optical technique, very easily to combine with Raman, optical, fluorescence, imaging. Since we are in ambient atmosphere, it is much cheaper, much easy to use, and you can scan very large surface also. It's not a big deal with that. And more importantly, I did not talk about that, but this technique here, LA-ICP-MS, XRF in general, they are not sensitive to light elements, carbon, lithium, hydrogen, and so on. This other technique cannot see them because of flake in terms of sensitivity, while for us, that's the best elements. Lithium, for example, we can go in the hundreds of ppb level. That is quite low. Okay. Some specificities. In general, when you will heard about LIBS, most of the colleagues in the world, they are using big laser with tens, hundreds of millijoule, and that we're focusing very big energy in, and you have, let's say, even almost a centimeter scale plasma. That's the left side. And what we are doing here with micro-LIBS, basically we are using a strong numerical aperture. It's not huge, but a high numerical aperture objective. And as you can see, we have an almost perfect recovery between the incident beam and the plasma that you are generating. And this is very cool because your plasma will be much more homogeneous than here, where in this case, the energy is bring to the plasma center, while here, the energy is more homogeneously distributed. So we have a better atomization, better homogeneity. The second point, when you are doing micro-LIBS compared to more conventional LIBS, is that you have a plasma that is very tiny, is in the range of several hundreds of micrometer. And so it is much more easy to collect in a more efficient way the lights. That's as small as your light source. Wow. Smaller your light source, bigger will be the collection efficiency. All the plasma is collected. And then this is maybe one of the more, the 2 or 3 slides are quite important because you will see all the limits of this imaging technique. The first one is if you want to consider the performance of this imaging, we have to consider the resolution, the sensitivity, and the speed. So the first things we can say on the resolution is that we want to work in the configuration for which there is no overlapping between consecutive laser spots. So that means that if you shot one time on your sample, the damage that you have will be the ultimate resolution. And this damage is coming from the ablation itself, for sure. That's the hole that you have here. But you have two also other effects like the shock wave formation, as I say, thermal diffusion on the sample. And in some cases, these side effects can damage the sample much more than the ablation. It will depend on the sample. So in this case here, we have a thin tissue slide. It's a 10 micrometer thick tissue put on a substrate. So you can imagine that this is very fragile sample that will be strongly affected by shock wave. And this is what we see here. The damage induced by the shock wave, it's much bigger than the ablation itself. So depending on the sample, we will have to adapt the ultimate resolutions we can obtain. But in general, for most of the materials, we can easily reach a resolution of 20 micrometer, very easily. The second thing is related to the resolution and to the sensitivity. Why we are working at 10 micrometer while we could focus the beam much more? It's very easy. More you ablate material, more you will have emitters, and more you will have signal. So there is a balance between the amount of mass that you remove, and so the ultimate resolution you can get, and the signal. So you have here an example. If you reduce the crater size, the limit of detection increase very quickly. And so I was always going in the direction of the sensitivity. And this is why we have selected to work here in the range of the 10 micrometer spots. So it's like you ablate a cube of 1 micrometer square. And in this configuration, we have such type of limit of detection. So for example, lithium, beryllium, sodium, calcium, magnesium, strontium, we can go to sub-ppm. It means that in one shot, we can observe a proportion below 1 million in weight percent. For metals, in blue, you can easily reach a few ppm to tenths of ppm. So it's not so bad, it's quite good. For most of the metals, you can reach the 10 ppm, still in one laser shot. Unfortunately, for halogens and organic, this is dramatic, especially for halogens. It's because all these elements here have a very high excitation level that we don't have. There is enough energy to excite them properly. So in this case, we are more in the percent scale. But let's say magnesium, for example, as it is shown here, a fraction of nanogram of ablated matter, 1 ppm limit of detection, it gives you an absolute limit of detection in the range of a fraction of femtogram, hundreds of attogram in one shot. So this technique is not so bad. And finally, the speed. As I say, we are working at 100 Hertz, that are all tabletop instruments, blah, blah. And also the second point is that we are using intensified CCD detectors here. So you have to read all the CCD matrix. And this takes time. So you can, you can basically use a mode that it is called a full vertical binning mode. It means that for each row here, all the charge are accumulated and read. So it means that you don't read exactly your matrix in terms of image, but only in one spectra where each row is accumulated. It's a full vertical binning mode. In the current model of such ICD detector, you can operate this full vertical binning mode in 100 Hertz, but you cannot operate it at 1 kilohertz. If you want to operate only at 1 kilohertz, you have to select only few pixels in height. And so it means that at 100 Hertz, you can benefit from all the lights upcoming here from a bundle of 19 fibers. While if you want to use it, the kilohertz, you only have one fiber. So you can go faster, but at the price of lower signal-to-noise ratio, lower signal. That's also a balance. So I first aim to show you many applications, but I was thinking that this lecture will be a nightmare for you if you have two slides. So basically, I only show you in the following an example with medical application. And what you have to know, if you are not familiar with that, is that in hospital, if you are doing surgery, the doctors take a part of the tissue that was removed from the surgery. They process them with sample fixation using paraffin. It allows you to conserve the tissue for many years. So this is a paraffin embedding. And then the traditional way, the more conventional methods, is to make a thin slice of the tissue and add a coloration called HES. That will be then observed with optical microscopy. This is called histology. And so we have some histology pathologists, I don't know exactly the term, clinicians, specialists on tissue that will observe with microscope the structure of the tissue, the physiology of the tissue, and they will say, oh, you have a cancer, you have no cancer, etc., etc. In some cases, if the clinicians are suspecting intoxication with exogenous elements, they can ask for MEB analysis, SEM analysis. And so a part of the tissue is sent to a SEM-ADX, and they do some punctual measurements to detect if there is some particles and so on. So, two examples. The first example is a lady of 50 years old that received an implant in the elbow. And 5 years after the implants and the surgery, she was very harmful, and she got back to the hospital, and she was suffering from a severe inflammation of the tissue. The doctors asked to remove the implant and replace it. And so they collect the tissue as the vicinity of the implants. And so this tissue was analyzed by all the techniques present in the hospital and in some laboratories. The histology reports report this. So the membrane is free, fibrous, and compact, no inflammatory, no particle is detected. They made some SEM measurements with no results at all. And so we made LIBS. Of course, it's not fantastic image, but we were able to observe signal coming from all the components of the prothesis. So the titanium alloy, cobalt chromium alloy, even of the pyrocarbon here. And since this was not observed in optic with histology, we can strongly consider that this is nanoparticles that came from the friction of the different components of the prothesis. Second case is more complex, but also I very like this case for a reason. That's the first time where LIBS is used by the assurance maladie, health insurance. Not bad. So I explain you the story. This was a lady of 60 years old that get a lung transplantation because she was suffering of very, very strong emphysema and so on. And it was a passion of Vincent Bonneterre, professor in the CHU of Grenoble. And Vincent was suspecting an intoxication with agent related to the history, the professional history of the patient. And so he made a lot of tests, ICP, SEM, etc., etc., and none of the techniques were able to reveal any metals. And so we got this tissue, we made the analysis, and this is the results we got. A very, very strong amount of silicon, aluminum. So it means that, let's say, aluminosilicates. And we compared this strong signal with some references. So let's say normal tissue, that was not easy to get. This is another story. And we can see that there is 2 orders of magnitude stronger, bigger signal of these elements, clearly showing there is a problem and strong intoxication with these elements. And it appears that this lady, during, also when she was like 25 years, she worked during 6 months in a ski station with sun and strong sabling, I don't know, sanding for the ski. And she was like breathing a lot of sands. So these results were used by the health insurance to transpose his disease in professional disease. So I think it was 3 years ago. Since this moment, all the disease was taken in charge by the company and not from her pocket. Sorry, 2 hours in English. So we are also very lucky because there is a new stuff, a new first time. We are now it's from 3 years ago, but we are initiating a prospective clinical trial with LIBS, that is the first one, with rare lung disease like emphysema, sarcoidosis, and we are collecting samples from 10 hospitals in France, analyzing the sample and so on. Also creating a database, a biobank, so that was possible with a strong discussion with the medical institutes in Grenoble. So for each biopsies, they collect some sample for us to make like a kind of reference. And up to now, we analyze 100 of sample, maybe 150 sample now, and we have like 100 millions of LIBS spectra on this type of sample. So the interpretation is not easy, but for sure, now what we can see is that for most of the patients, we see a much stronger signal for elements such as silicon, aluminum, titanium, copper, and chromium. So it really means that these diseases that are idiopathic, it means that we don't know the origin of the disease, maybe related to strong accumulation of some metals. I don't know, I'm not expert on that. Okay, so now I'm going to the part that is maybe not the, no, it's very nice part, but honestly, imagine that you have an equipment that is doing hyperspectral imaging. So you made imaging, and for each pixel of your image, you have a spectra, a full spectra. And that you have, for example, 10 millions of spectra, a big files that is half teraoctet. I give you this file and say, okay, process the data. What you will do? So honestly, I got some nightmare. Because the first image, you remember this garbage image on the left, very small, few pixels. In fact, there was like 30 by 30 pixels. So it took like all the day at this moment to make the measurements and all the night to process the spectra and the image. I say one time, but not every time because I will die. So we have to develop some tools. I don't know if it's the best tools, but we have to develop the capability of processing the data. If we increase imaging, now, I will show you in perspective, but now we can record 1 million image, 1 million pixel image in 17 minutes. So 10 million in less than 3 hours. But there is no really sense if you do that, if you need 1 year to process this data. So if you increase the instrumental speed and so on, you also have to work on the processing because, yeah, you have to balance both. And the data processing is a key factor. It caused me a lot of nightmares, honestly. And I will show you why. You will see all the complexity also of this technique. Here you have a, I think it's nice, no? It's an optical image of a sample collected in Morocco, I think, where you can see different mineral phases just by the color. You can see here how the sample is complex. Also, you just have 3 or 4 colors. If you look at the LIBS, it's almost the same. You can really see all the structure of these minerals, very small grains. So it was just to show that by nature, most of the samples that you want to image are already very complex. That's the first point. And here, there is another example where you have 6 mineral phases. So there is a small video I have to explain you before starting. So what you have here is the average spectrum of all these analyses. And then when I will activate the video, you will see a cursor that will move to the right and the image on the background that will correspond exactly to the wavelength of the cursor to show you the complexity, in fact, spectrally. As you can see, there is a lot of image. Sometimes at one wavelength, there is superposition of several contributions, means that you have spectral interference and so on. And it was a pure hazard, but the last pixel here show the distribution of rare earth elements, yttrium and lanthanum. So the sample is complex, first point. Second point, we are working with emission spectroscopy. So we have to deal with emission spectroscopy. And in emission spectroscopy, there is good atoms, very good one, like magnesium, silicon, aluminum, calcium. There are other, but they are good. Why they are good? Because you have well isolated lines, strong lines, perfect. These are good atoms. And you have awful atoms. Iron. Iron is awful. Honestly, this is awful. It's several thousands of lines everywhere. But there is no iron. All transition metals like titanium, chromium, nickel, also you have thousands of lines. And so this is the difference with XRF. In XRF, in the maximum, I think you have 2 lines per element. But the lines are quite broad in XRF. Here we have much narrow lines, but in some case, you can have thousands of lines that even the database does not know in some cases. The second point is that we have matrix effect, as I say. And so the matrix effect will be related also to the plasma temperature, electron density. And so in some cases, you can observe 2 very different spectral signatures from 2 different matrices. But in fact, this is the same elements. And this is the case for iron. Here, in red, you have a hot plasma, the signature of iron. So this is mainly the ionic lines of iron. While in gray, you have low temperature plasma with mainly the atomic lines of iron. So each line, each element will move depending on the fluctuation of your device, the matrix, and so on and so on. So first is the sample is complex. Second, the emission spectra may be very complex. Third, in fact, we have a problem that I did not talk about. It's not very a problem, but it's physics. Imagine that you have your plasma. Inside your plasma, you have an emitters that send you photons. And it sends you the photons in the direction of the detection and the collection. But on the travel, on the journey, this photon is absorbed by a surrounding atom. So this photon never reached the detector. And it means that higher will be the concentration of the elements of interest in your plasma, higher will be the number of photons absorbed during the journey of the photon through the detector. This is called the self-absorption. And this self-absorption makes that the intensity is not linear to the concentration after a certain concentration of your elements. So this is typically what you have. After 1%, you have a saturation of your intensity signal. And this is not very good for analytical application, but for us, this is very good because we can then extend the dynamic range of measurements. If you look here, we have with our ICCD detectors like 4 orders of magnitude in terms of detection range. With this self-absorption phenomenon, we can then go to 6 orders in terms of concentration. So it means that on the same spectra, you can observe 100% and 1 ppm. Just to say that these 6 orders of magnitude is the difference between a B and the eVREST. It's huge. It means that the spectral complexity that we saw with all the line and so on may also be reported in the vertical axis, because in the vertical axis, you may have very weak signal, and very strong signal. And so you have to look at all the scale of your signal. So LIBS imaging is the most complex hyperspectral method. And now I have to hurry a little bit because time is passing. So an example, 10 millions of spectra that can be recorded in 3 hours with the kilohertz instrumentation, 4 spectrometer. It looks like if you want to look all the spectrum by your eyes, you will need 5 years. With the French time, you have the holidays and so on, the weekend, the nights. 5 years if you want to see each spectra by your eyes. So it's not possible. We need to find new stuff to process this. And so there is basically 2 strategies. The univariate strategy, I will go back later on that. The multivariate strategy, so for this we are working with Ludovic Duponchel from the Lille University. He's professor, very famous professor in chemometry. And he tried to apply the principal component analysis, MCR, clustering, ICA, blah, blah, blah. It works very well, but you need a strong expertise in this data manipulation. So if I go back to my expertises, that is spectroscopy, we have developed a software to process this data. And this software is called the LASMAP. So the first step is you take all the spectra of your data set and you make the average spectra. That's the first step. From this average spectra, you identify the lines and say, okay, here we have some tin, aluminum, silicon, and so on. And we create the first image. And from this first image, we can create some mask. So, okay, in blue, we have aluminosilicates. In red, we have strong tin signal, and we dissociate from that. And so we have 4 different regions of the image. So we will calculate the average spectra related to each of these masks. And we continue, second iteration. And so now we are in the mask of the tin. This is the image of the tin with the optical image. So we apply the mask of the tin and we will look for other elements in this region only. And there you start to see quite interesting features, like with grow layer, with titanium, even with tungsten. And then we export this image in, let's say, text format to TIFF format, and we can use ImageG. This is the standard procedure for us to merge different colors of this image and provide the measurements to the user, in this case, the geologist. And there is an important competence to get, is that you have to, when you discuss with someone that brings you a sample, you have to really understand what the user wants. Because I could send to the user this 10 millions of spectra and say, manage it by yourself. Or no, I can make a synthesis of the results and get him only what he would like to see. So there is the univariate method, the multivariate methods, but both of them really need strong expertises. And imagine that you want to deploy a LIBS imaging instrument in the hospital, and you cannot form the doctors in both of these approaches. So this is why in the last years, we have been working in the development of artificial intelligence. So basically, we are using artificial neural network in 2 versions. Let's say simple case, complex case. Here, I will only focus on the simple case. So we have some materials of interest. In this case, this is archaeological mortar. And we want to identify different minerals in this sample. So basically an artificial neural network. I'm sure that you are familiar with this. Each neuron is a simple operation, and then you make the sum, apply a bias, and you go through an activation function that is sigmoid here. And then for this archaeological motor, this is a big project in archaeology. We collected a lot of reference samples. So carbonate, silicate, quartz, charcoal, many things. And we create some reference spectra. So for each of the classes we want to identify, we got like 200 of reference spectra for each classes. And then we made some learning of the algorithm to force to the algorithm to identify the different category of spectra and so on. And then we close the algorithm, and the magic occurs, honestly, because you send only numbers to your algorithm, and the output is image. And you have here a direct analysis of this sample, where you can see all the silicate, quartz, teal carbonates, and so on. That is really close to the reality. So these results were managed by an expert in archaeology, and he was very enthusiastic. And more importantly, this result was recorded before COVID. And we applied exactly the same algorithm to this sample that was recorded after COVID on a different instrument. And we got perfect results. So this method is very robust. So now I will give you the best idea I never had. Imagine that now you don't want a very simple algorithm that is able, to identify a quartz from a carbonate. You want a more general algorithm able to process any configuration. So you can expect to have a much bigger algorithm in terms of number of neurons, layers, and blah, blah, and so on. And so then you need much more reference spectra for the training. And at one point in LIBS, it is not possible because we don't have the sample. We cannot buy a sample to say, I want this proportion here. No, this is not existing. So the idea was to make some spectra simulation. Of course, we can create some reference instrumental spectra, but we will also add to our reference spectra from simulation. And we applied this idea in the case of this sample that is a stalactite. You cannot see it well, but it's blue stalactite. And just to show you, I select this sample because we got ablation issue on the left bottom part of the sample, as you can see here. And this is the normal calcium image of this sample. If we apply now the algorithm that was trained with simulated spectra, this really go back perfectly with a strong compensation of the region that was affected instrumentally. So it's very positive. And I'm very glad to show you the first image in LIBS domain. That reduced a little bit more of the stuff, but that were only processed by the machine and by the intelligence. So you have the magnesium here and the copper here. That is very similar, that are very similar to the initial image, but that are corrected in terms of stability. And more importantly, the value that you have, well, you cannot see, but the value of the pixel is concentration and not an intensity. That this allows also to get rid of the matrix effects, because in your simulated spectra, you will process this at different temperature, electron density, and so on. Okay. Next, Look at that. Kilohertz instrumentation, I think this is the future. Very simple laser, not very cheap, but cheap laser, cheap spectrometer, and you can get such type of image in a very reduced amount of time. So for sure, if we are able at term to combine such type of instrument with artificial intelligence, that will be for sure the future of LIBS. And you will see, I hope, some LIBS in your laboratories in a few years. But if we are not able to combine this with automated processing, that will be much more complex, because you need a strong expertise in the processing of these spectra. We are also working in optolysis with ANR in the development of a totally different instrument that is using UV laser pulses, and with the idea to image the distribution of lithium in electrodes. And that we got the first good results just before the holidays, with the capability to reach the 2 micrometer scale. I want to thank all the team, the spectrobio team in the ILM, the ANR that was very generous with us, a lot of colleagues that is very excited to work with them, and for sure, you for your attention.